Okay, last week we talked about the control protocol at the IP layer. We talked about the ARP protocol, ICMP protocol, DHCP protocol, and those kind of control plane protocols. We also talk about unicast routing, including RIP, OSPF, and BGP, where we see two kinds of routing strategies. One is called distant vector routing, and the other is link state routing. In the distant vector routing, we only exchange with neighbors, the distant vectors. Within the distant vector, we put things we know. I mean, the router knows. Perhaps any destination in the network. So the distant vector, there could be n entries in the distant vector, where n is the number of routers or networks within a domain. Within a domain. Okay, so that's a distant vector. So we try to tell our neighbors what we know. Okay, by just exchanging with neighbors, the distant vectors. On the other hand, the link state routing, which will broadcast the link state, where each router in the network would broadcast the link state to its neighbors. Suppose the router has 3 neighbors, so the link state would have 3 links. So it would tell every router in the network the link state information of his 3 links. And because every router would broadcast the link state, so every router would eventually, well, pretty quickly get all the link state in the network. By combining the link state in the network, it will be able to construct the topology, the topology of the network. So in link state routing, we have the entire topology of the network. So with the entire topology, then we could compute the shortest path with the Dijkstra algorithm. Okay, within just one iteration. On the other hand, for distant vector, you would need to exchange with neighbors. So there'll be many iterations for the information for the distant vector to propagate to all router in the network. So if the diameter is d, then the diameter of the network is d, then it would take d iterations for the distant vector to converge. And because you don't have, even with this, you still don't have the whole topology of the network. So you cannot compute with the Dijkstra algorithm for the shortest path. And instead, you would need to use a Bellman-4 algorithm to compute the shortest path. Okay, so that's the difference between link state routing and distant vector routing. And as we have shown that in the intra-domain routing, where within a domain there could be usually 256 networks or subnet, 256 subnets within the domain. So the size is not too big. So we could use either Dijkstra or Bellman-4 algorithm. And as we have seen, that we use a distant vector for RIP and Dijkstra for OSPF for the intra-domain routing. However, in the inter-domain level, because the network is so large with tens of thousands of domains, So you couldn't use link state routing. You couldn't use a Dijkstra algorithm because it's not scalable. It couldn't scale to that size. So you can only use a distance vector with the Bellman-4 algorithm. Okay, so that's what we see in BGP. And in BGP, we instead of using a distance vector, we use path vector. The difference is the path describes the entire path. Suppose the path needs to traverse 10 routers, then you would need to put those 10 routers in the path. So you exchange with your neighbor router with path vector instead of distance vector. The reason is because you don't want to have loops within the path. So every router, when they receive the path, it would check to see if I'm in the path, then there's a loop. If my ID is in the path, then there's a loop if I use this path. So by a simple check, you will be able to see whether there's a path, there's a loop in the path. So that's why we use a path vector instead of distance vector. Another reason is because in the backbone, in the internet backbone, for the interdomain routing, the backbone router could be disjointed apart. Could be several hops away from each other. So so you wouldn't finding the eliminating the loops is not as trivial as intradomain. So you need to explicitly put the path in the vector you exchange. Okay, so you exchange path vector so that you can examine the loops explicitly. Okay, so after talking about intradomain and interdomain routing, that's unicast and which we use every day, we next look at the multicast routing. And as I said, IP multicast is not a successful technology. In fact, you could say that it's a kind of failure, and the reason is because it would change the stateless nature of routers, and we will see that you would need to keep some state in the routers in order to do IP multicast, which is bad, and that's why it is not successful. Today, you will see some application running on top of IP multicast, but only at a limited scale. For example, in this university, we do that only for the campus area, campus networks, not on the backbone. So it's very limited. It's a local, and for the purpose is for IPTV, especially when there are sports events. Then people might want to watch on the internet instead of on the cable TV. Then then you would use IPTV, and that IPTV, in order to be scalable, so that you would have only a stream instead of many streams. Say I have 300 people watching the same video, watching the same live sport event. 300. You don't want to pump 300. You don't want to pump 300 streams from your server. Instead, you just want to pump one stream from your server, and the router will multicast to the 300 receivers. So that's what the IP multicast does. However, we don't do that in the backbone. In the backbone, you will see another technology called application multicast. Application multicast, where you would have servers doing the multicast. In fact, a hierarchy of servers doing the multicast. So the root server will unicast to several servers, the second level server, and the second level server will unicast to a third level server, and then the third level server might talk to the client. So you would have a tree of servers, and between the node within the tree, the stream are unicast. But as a whole, it looks like a multicast because the root server only unicasts once or one or several limited number of streams. So that's called application multicast. In the sidebar, I think in this chapter, in the sidebar, there's a sidebar. there's a sidebar in this chapter comparing the application multicast with IP multicast. You can take a look to see the difference. Okay, so again, at a backbone, you do application multicast because you don't want to put state on the routers, on the backbone routers. However, in a domain, within a domain, you could do IP multicast. And again, you will put state into the routers. The router needs to keep the state for those for the router within the domain, which might be okay because they are not backbone router. They don't need to handle tens of billions of packets per second. Okay, but in the backbone, you don't want to do IP multicast, and we will see that what kind of state should be kept in the router if you do IP multicast. Okay, so I'm going to start with the basic protocol, which is called IGMP, Internet Group Management Protocol, which is the abbreviation is similar to ICMP, but they are of course quite different. ICMP, we have seen that it's for control. It's a error reporting. It's an error reporting protocol. Here, IGMP is membership management. It's about group membership management protocol. And then there's many multicast protocol. The most common two are DBMRP and PIM-SM, sparse mode. You will see PIM have two versions. One is sparse mode and one is dense mode. And we will see the sparse mode. And then some other new stuff. And then the real system, which is called backbone, MBONE, which run DBMRP. So MBONE run DBMRP. However, I will not talk much on this because there'll be create more confusion to you if I talk further on that. So I'm going to talk about IGMP, the concept, and compare these two, DBMRP and PIM-SM. And so by definition, multicast is to communicate among more than two parties. So multi-party, it could be multi-party conferencing or distant learning or watching the live TV program. And the issues are how to maintain the group membership. Suppose, and we will use Class D IP address. The Class D IP address is, the address space is reserved for multicast, IP multicast. And so we will use that Class D. But, so when we send a packet with a destination IP address being a Class D IP address, it means that this packet is a multicast packet destined to a Class D address. However, when I send a packet to the router needs to know the membership, information about the membership. Okay, the router needs to know where to route the packet, where and so if I receive a packet destined to a Class D address, and from this port, and I have 3 other ports, should I route the packet to one of the 3 ports, or 2 of the 3 ports, or 3 of the ports? So that's a decision I need to make. So to make that decision, I need to know if I have a link. I have a 4 link. The packet comes from this link, and I have 3 other links. And I need to know whether on this link, are there any members of this Class D address? And again, for this link too, I need to know, are there members of this Class D address? And for this, the same. So I need to know whether there are members along these 3 links. If there are, then I forward. And suppose these 2 links have members in that direction belonging to this Class D address, then I would forward a packet to these 2 links. However, I would not forward the packet to the 3rd link, because there are no members belonging to this Class D address. So all I need to know is whether there are members in this direction. Okay. So, but how do I keep those membership information? How do I collect those membership information? And those members, they are at the edge of the network. They are the host. And we know the hosts are at the edge of the network. And how do I collect those member information? That's the first issue. And the second issue is, how do I form or construct a multicast tree for packet transmission? How do I form a tree? Do I need to explicitly compute a tree? Or is the tree formed automatically? So is the tree formed explicitly or implicitly? Okay, that's the second issue. And the third issue might be minor, but still an issue: the many-to-many communication. If there's a group with 10 members, any of these 10 could be the source, could be the sender. So those 10 members, they could be sender and receivers, and they can sometimes be sender, sometimes be the receiver. So so it's a many-to-many multicast scenario. So within a group of 10, it's not a particular host who is always the sender. There could be others who can be the sender. So it's a many-to-many scenario. And how do we do that? Resolve these 3 issues? The first issue can be resolved by the IGMP protocol. And here's how it works. It is used by IP host to report multicast group membership to the router. So it's for the host it's a protocol between the host and the routers. So the router so the host needs to tell the router that I am a member of which group. Okay, and let's take a look at how it works. A router which is capable of multicasting will play one of the two roles. One is a querier, and the other will be non-querier. The querier is the router, means the router is responsible for maintaining the membership information. And if on this subnet there are multiple routers, then one of the routers will be the querier. And which one? The one with the smallest IP address will be the querier. So this router will be in charge of this subnet. If this subnet has multiple routers connected to it, then the router with the smallest IP address would be responsible as a querier. And what does the querier do? What does the querier does this, periodically send a general query to solicit membership information. and this membership information, this query is sent to this is IP multicast address. This is IP multicast address. And of course, this query in the MAC header, in the destination MAC address, it should be broadcast. So this query will be broadcast at a link layer with the destination MAC address filled with all ones, so that all hosts on this subnet will get this message, get this query. And at the IP layer, this query message would have a destination IP address of this. It's a IP multicast address, class D address. So I'm a router with the smallest IP address on this subnet, compared to the other routers connected to this subnet. So I'm responsible. So I should periodically send a query asking the host. I'm broadcasting to ask the host, okay, does anyone belong to a certain class D address? If you are, then send me a response. So so it would explicitly solicit the membership information. And when a host receives the query, it would do this. Okay, so I broadcast on this subnet asking who belong to certain members, certain group, who belong to certain group. And the host, once received this query, it would send report. It would send a report specifying who I am, specifying what IP address, what class D address I belong to. Okay. However, there's a trick here because on this subnet, if there are 10 hosts belonging to the same class D address, if there are 10 hosts belonging to the same class D address, meaning belonging to the same group, then all of them, 10 of them will send a report, will send a response back to the router. However, the router only needs to know, do I have a member on this subnet? It does not need to know who and how many. I only need to know whether there are members on this subnet. They are hosts on this subnet belonging to certain group. I only need to know this because if there's a multicast IP address coming in, then I would forward a packet here and set the destination MAC address as broadcast address. So they will get it. and I don't need to say send it to unicast to each one of the 10 members. So, and the reason why I only need to know whether there are members belonging to a certain class D address. I only need to know this. I don't need to know who and how many. I just need to know whether there are any. The reason is because remember in the router, in a network of routers, if I'm a router and I receive an IP packet with a destination with destination IP address as a class D address, and I have 3 other links, I only need to know, do I have members in this along this link? Do I have members along this link? I don't need to know who they are and how many. I only need to know, do I have member on this link? If I do, then duplicate a packet to that direction. So that's why we only need to know whether. We don't need to know who and how many. Okay, is that clear? I only need to know whether. If there are none, so knowing if there are no members belonging to a certain group, or knowing there are members belonging to the same group, I only need to know this. I don't need to know how many. And knowing there are 10 members on this subnet is the same as knowing there are members on this subnet. Okay, so so now there's a trick here. Instead of when the host receives this query, if I don't do something tricky, then I will get 10 responses, because each one of them will respond, and I don't want that to happen. And perhaps worse, if there are 100 members on this subnet for a particular group, then all of 100 hosts would respond, which is bad. So there's a trick here. So every host, when they receive the query, they will delay a random time. Okay, there will be a delay of random time. And when the timer expires, it will pick a random time. And then when the timer expires, it will send a report. The report will say that, okay, I belong to a certain class D address. I belong to a certain class D address, and I want my router to know that there are some hosts belonging to a certain class D address. And I set TTL to 1. It means that it is only between me and the router, and TTL will be deducted by 1, as we know. At each router, TTL will be deducted by 1. So when it reaches 0, then it's done. It won't be forwarded further. And this is called, there's a mechanism called report suppression. Okay, and when I'm sending the report, I send it in a broadcast mode. So I broadcast the report on the subnet. So all the other routers also receive this report. All the other hosts will receive the report, my report. I'm a host now. Suppose there are the other 99 hosts belonging to the same multicast group. Then if another host, so when I'm waiting for my timer to expire, if there's another host report, if I receive another host report saying it also belongs to the same multicast group I belong to, then I will stop the timer and do not send the report. Okay, so that's called report suppression. So the first one who sent a report, okay, the other 99 will suppress because they hear the report. they hear that guy send a report saying it belongs to the group. So the other 99 who belong to the same group would suppress their report. They know that, okay, somebody has spoken for us through the router. So we don't need to say it again. The router has known that there are people belonging to that class D address. So we don't need to repeat saying that again. And the router only needs to know whether they are hosts belonging to that class D address. So this report suppression is done by a small trick like this. So everyone pick a random time and then wait. And the time doesn't need to be long. Perhaps several milliseconds will be enough. Okay, because it's in the subnet, so it will be very fast. So within milliseconds, it would do that. And once there's one who sent the report first, saying belong to this class D address, the other hosts who belong to the same class D address will suppress their report. Okay. Similarly, the router could send a general query or a group-specific query. A general query means that, okay, anybody belonging to any group. And group-specific query means it sends a query asking anybody belonging to this particular class D address. Okay, so it's a group-specific and general query. And when the router receives a report, it would add a report it will add a group being reported to the list of multicast group. So it would maintain a list. Okay, I have, for this particular subnet, I have people belonging to this group. I have people, so there's a list. If within the list, it says 3 class D address. It means that there are hosts belonging to these 3 groups. Okay, so I'll keep track of that. And I set a timer for each of the entry, for each of the group. So I set a timer, so it would expire. So if I send a query and I got something, some information, group membership information, and I set a timer, if I ask again next time, nobody answer, and the timer expires, then that group membership information will be deleted. So the membership information is a soft state. It's a soft state, not a hard state. Okay, it needs to be refreshed. And the refresh mechanism is done by periodically query. Okay. What about can a host join a multicast group proactively? Does it need to wait all the time for the query from the router? It could. It could send an unsolicited report immediately. So if a host wants to join a multicast group, I want to join this, and I don't know whether there are people, whether there are hosts who have joined that class D address already. I don't know whether the router has known that already. I don't, because I just joined recently. Then I would send an unsolicited join message. I'm telling the router proactively that I want to join a particular group. So in that case, then the router will keep track of this group membership information if it's new to him. It's possible that the router have already known. I have already known that there are hosts belonging to that particular group. So you tell me again, and that information is kind of redundant, which is fine. Okay. But if there are no hosts belonging to the same multicast group, then this information is very useful. It will be useful because you are the first who belong to that particular class D address. How about a host leaving a group? Okay. It says that if the host is the last host to reply to the query, okay, so it is the one who replied the query, and if this particular host wants to leave a multicast group, then it should send a leave group members. And the leave, so it would tell the router, I'm leaving this group. But can the router remove the group membership information immediately? Can it do that? No, because there might be other hosts belonging to the same multicast group. So, so the router would do this. It would send a group-specific query every certain time. And if there are no report received for a certain number of time, then it would remove the membership information. So, so when a particular host wants to leave the group, and it is the host that sent the join message last time, it would need to send a leave message. And when it sends a leave group message, the router does not remove the membership information immediately. It would need to wait until it got no response for several times of queries. And then it makes sure that there are no groups. There are no hosts belonging to that particular group. Then I remove my membership from the list. Okay. So that should pretty much, so consider this, all the hosts are at the edge of the network, and each host will belong to a certain subnet. Okay. And on a certain subnet, there's a router who is in charge of the group membership management, and then it will be the querier. And if there are multiple routers on this subnet, then the router with the smallest IP address will be the one in charge, which is called querier. And it would need to send a query periodically. The query is broadcast on the subnet, asking whether there are people belonging to any multicast group. And when the host receives the query, it would respond, but before it responds, it would pick a random time and wait for random time and then respond. But during the random wait, if there are other hosts who send the group member, who send a report to the send a response to the query, it would listen because the response is also broadcast. So it will get that and see, and it will check that and see that whether there are other hosts reporting belonging to the same group I belong to. If there are, then I suppress my report. If some other host already report they belong to a certain class D address, which is the same as the one I belong to, then I suppress my report. Otherwise, I will, when my random wait is time off, it's time out, then I would send a report. And on the edge router, connecting to the subnet, they will know whether they are hosts belong to certain groups. And they keep track of that information. And that information is soft state. It would time out. It would time out after several queries without without being refreshed. It would time out. Okay. And how about, but we only solve the problem of the age of the network. Only the age router would know the group membership information, right? Not the non-age router. Non-age router means that they are not connected. I mean, they are not connected to a subnet with host, right? So for those backbone router, I mean, non-age router, they still don't know the group membership information. They don't. And how does it work? We'll see that pretty soon. But at least we now, with the IGMP, we now enable the edge routers who are connected to the subnet with host to be able to know to be able to keep track of the group membership information. And see, this is a very simple IGMP message format. And here is a class D address, multicast group address, which is class D address. So when you send a general query, then you don't fill up, you leave it empty. But if you send a group-specific query, you need to specify the IP address here. Or on the other way, if you send the report, if the host sends a report, it would need to specify which class D address it belongs to. Okay, and here's the type. It could be a general query, group-specific query, or membership report, or lib group message. And it could specify the maximum response time. The router could tell the host, okay, within this, you can do a random wait within this time period. So the maximum response time or maximum random rate could be specified here, and also the checksum. Okay, I skip this. Okay, then how does it? We only enable the edge router to keep track of the group membership information, but for the non-edge router, they still don't know. And how do we work with that? So we see the multicast routing protocol. We would only look at two of them. In fact, there are two kinds of multicast routing, and it's called source-based tree, source-based and code-based. Okay, source-based and code-based. So the source-based tree means that if I have a group of 10 hosts, meaning I have a group of 10 members, then if any of the 10 could be the sender, then I have 10 trees. I would form 10 trees. Then that's called source-based tree. So there'll be 10 trees. But if I have 10 members, okay, let me repeat again. Okay, if I have 10 members and any of them could be the source, and if they are the source, if one host is the source, then it will form its own tree, multicast tree. Then it's called source-based tree. But if I only have one tree shared by the 10 hosts, so either one of them could be the sender, but when they becomes the sender, they would use the same tree, the same multicast tree. then it's called core-based tree or share-based tree. Share tree or core-based tree. And let's look at the source-based tree first, which is DVM-RP, and PIM-SM will sparse mode will be the core-based tree. However, PIM dense mode, DM is the source-based tree. So we would just look at the PIM-SM. So if we have a source-based tree, it means that we have, for a group of 10, we would have 10 trees. So it will be per source group tree. However, for core-based tree, you only have one tree for the group, so you would have per group tree. So if I have say, if I have 100 groups, each group has 10 members. Then for source-based tree, I would have 1,000 trees. Okay. However, for core-based tree, I would have just 100 trees because I have only 100 groups. So one is per source per group tree, and this will be per group tree. And let's look at the DVM-RP first. It is derived from RIP, which is unicast routing. And DVM-RP is widely used on MBON, which is a real system, real multicast backbone on the internet. And it used tunnel, IP tunnel, to do the multicast. And it constructs a source-based tree per source. Per source tree, per source per group tree. And it provides a shortest path between source and receivers using the so-called reverse path forwarding, RPF. And we'll talk about this RPF. So we look at the example here, which will be easier to explain. Now suppose we have a group of three. So you see the host. We have 3 hosts. Okay, belonging to the same class D address. And now the source in the yellow color, the source host, is going to multicast to the other 2 members, the other 2 hosts. And now the edge router, they got the group membership information. So these are edge router, they know that. And if there's another subnet here but no groups, no members belonging to this group, this router will know that it has no members belonging to the group. Okay, so now I send a packet to my router, and the packet has a destination to a class D address. Now what does the router do? At the beginning, it will flood to the other 3 links. And then the other 3 routers, the 3 routers receive it. And worse, this router receive a copy from this neighbor, and also receive a duplicate copy from this router. And then it needs to know that it needs to drop this packet, but forward this packet. But how does it know it needs to drop this packet? You don't want the router to keep track of the identifier. information of the IP packet in order to drop it. No, you don't want to do that. What you want to do is that you want to check whether the packet, the source of the packet, the source of the packet is this one, and I will check my routing table. If I want to go to this one, should I go to this port? It says no. The source of the packet, if I want to send a packet to the source of this packet, I should not, the next hop is not this. The next hop is this. So this copy is not on its shortest path. This packet is not on its shortest path. So I would drop it. And this kind of decision is called reverse path forwarding. So let me repeat it here. When the router receives a multicast packet, it would forward the packet on all of its outgoing links, only if what? The packet arrives on the interface that is also the interface of the shortest path back to the sender. Read again. If the packet arrives on the interface that is also the interface to the of the shortest path back to the sender. Okay, so it's on. If the packet is on its shortest path, then I will forward for it, and that's called reverse path forwarding. So if I got a packet from this link, and I check the source of the packet to see if I want to go to this IP address, if it's is the next hop, is the interface on the shortest path of to this particular host. If it's not, then I drop it. If it's not, it's because it means that the packet is not on its shortest path. And in a sense, so this is, so I'm saying this packet, the source of this packet is this one, and the shortest path to that packet, to that host is through this interface, not through this, so I drop it. And there's an assumption made here, that I forward this for this packet because the source of the packet is that one, is received on the interface that is on the shortest path back to the source. So I imply that the shortest path from the source to me is the same as the shortest path from me to the source. So I'm sending I have made the assumption that the path is symmetric, meaning the shortest path back to the source is the same as the shortest path from the source to me. I have made that assumption. Otherwise, it would suppose in the worst scenario, okay, if the shortest path from this router to the host, this source is this, but the shortest path from the source to this will be this, not this, then my assumption is incorrect. So if the shortest path is this, in this direction, but in the other direction, the shortest path is this, then I'm assuming I drop this packet, which is incorrect. Instead, I should drop this packet, but forward for this packet. However, fortunately, in a small area, in most cases, the shortest path is kind of symmetric. But in the backbone, it's not. in a backbone internet, the shortest path from X to Y is probably not the shortest path from Y to X. But in the local area, the shortest path from X to Y is most likely to be the shortest path from Y to X. And if the assumption is correct, then I'm doing the right decision by dropping that copy. Okay, is that clear about the assumption, the symmetric shortest path, and why we drop one packet? I mean, why we drop this copy? Okay. Okay, this is the same for this router. I receive the packet from this. I check the source of this packet. Is it received on the interface of the shortest path back to the source? I look at my routing table. It says yes. The shortest path to that source is this. So based on the assumption of symmetric shortest path. So I'm using the shortest path in this direction as the shortest path of this direction. So I will forward for this packet. So I forward. But again, if I receive this copy and this packet and it says the source is that one, I check my routing table to find out the shortest path to this source is through this, not through this. So I will drop this packet. So keep doing that. You will see the frauding will be limited. Okay, and this router would not fraud there, but it would fraud here and here. And eventually it would reach the members. However, there's a problem. What problem? Now you got redundant frauding here, right? There are no members. But you fraud. And it should be what? Prompt. It should be cut. You don't want the frauding here. You don't want the frauding here because there are no members here. So what you would do is this. You would send the prompt message. If this is the edge router connecting to a subnet, but this subnet has no members belonging to this particular class D address. And I know that. And I have received that, and I find I have received this packet. And I check my membership list. I check my membership list, find out no members belonging to this class D address. So I received this. I take the destination IP address, which is a class D address, to check my list, membership list. And I've seen none belonging to this particular class D address. So I know that this router, my upstream router, is sending me something redundant. So I will send a prompt message telling, don't send me more packet destined to this class D address. Don't send me more, okay, to this class D address. And again, when this router receives this, it would forward back to the upstream. Forward back to the upstream. So then this router would not fraud again once it received the prompt message. So it be cut here. So then I would have a clean tree, okay, without redundant frauding. Without redundant frauding. Okay. However, the default is true fraud. For the routers, the default is true fraud. unless I have a prompt state kept. I receive a prompt message and I need to keep track. I need to memorize that prompt state. The prompt state says that don't forward to, if you have a class D address, don't forward on this link. If you have a packet destined to this class D address, don't forward on this link. So it's a class D on this link, no. Okay. Then, so the default is true forward unless you have prompt state kept here. So the router needs to keep track of the prompt state. And that prompt state is what? Per group per source. Per group per source. It could be many states to keep. Again, the default is true fraud unless you have kept some prompt state, and the prompt state are per group per source. So you have this, and if you have, this is clean, which is fine without redundant forwarding, but these guys are keeping some state which is bad, right? We don't want the router to memorize something, but now they need to memorize the prompt state. So are the edge router. The edge router needs to maintain the group membership information they collected from IGMP. And the non-edge routers, they need to keep track of the prompt state. And worst of all, now this member is the source. What about this host decided that it needs to multicast to the other two guys? Then it will form another source space tree. And if this guy talk, it will form another source space tree. So if these three hosts, they all talk, then you would have 3 source space tree. And the router would have more information, more prompt state to keep, right? The router will keep more prompt state since it's per source, per group per source. That's a DVMRP. And why is it called DVMRP, distant vector? Because it relies on RIP. It relies on RIP use distant vector, right? RIP use distant vector routing. Okay, there are some drawbacks and benefits of this scheme. Let's see the benefit first. It guarantees efficient delivery, easy to implement. So do you need to compute the tree? No, you don't compute the tree, right? You don't. You just use reverse path forwarding. You take the unicast shortest path and use it in the reverse direction, right? in deciding whether you need to forward. Okay, so you don't explicitly compute the tree. And the drawback is that the first packet or the first few packets need to be forwarded. And there'll be periodic prompt state refresh. Otherwise, it would time out. And the routing state or the prompt state is per group per source. Per group per source. So it's a large number of state information to keep. If we use this scheme and the multicast traffic account for 30%, and the other 70% are unicast traffic, then you can imagine that there will be many prompt states to keep on the routers. Okay, so it says that it's not scalable, especially if it's a sparse network. A sparse, the group membership are sparse. What does it mean by having a sparse group members? It means that they are scattered far apart. say one in Taiwan, one in US, one in Europe, then all the router in between, they need to keep the prompt state. That's incredible, right? So apparently, if you use this on the backbone internet, it will be a very big overhead for the backbone router in between. Okay. So for the router between US and Taiwan and Europe, those router, I mean, on the path, they need to keep the prompt state. That's incredible. That's great overhead. So DBMRP will be used only for what? For the domain, intra-domain area, for the small network, because it's not scalable. So work well only for densely represented groups, and large amount of state in which to keep per group per source, and not scalable. So you would use it only for the intra-domain multicasting. How about PIMSM? It use the code-based tree, and I would use an example to explain. Then we look at the text. So again, we have 3 hosts in this multicast group, and there'll be one router who serves as the rendezvous point. Rendezvous point. I think this is French. Rendezvous point. RP. And DR, designated router. So these 2 terms. Okay, so we want to have a shared tree, a code-based tree. So there should be only one tree per group tree, not per group per source tree. So just one tree. Whether it's this guy talk, or this guy, or this guy, they would use the same tree, same multicast tree. So one of the router will become the rendezvous point, or the root point, the root router. Okay, but how do we decide that? How do we decide who is going to be the router, the root router, or called the rendezvous point? We use what? So if you have 3 guys who want to agree on something, pick something, and what would you do? And you know the multicast IP address, class D address. You use what? You put it into a hash function. You take the class D address and put it into a hash function, and you got a number, say 3. So router number 3 will become the RP, rendezvous point. So you talk, or me talk, or he talk, we would use the same hash function, and then we will hash to 3, router number 3. So we would agree that router number 3 will be the rendezvous point for us, for this multicast group. So that's by hashing. Okay, so that's the first thing. So so you would this is the root port, rendezvous point, or the root router. So you would send a packet to this RP router, and what you did is that you send the packet to the router. The host does not need to worry about that. It's the router who handle multicast. So the router, the host just send a multicast packet to this its edge router, and the edge router does a hash function on this class D address, and then find out, okay, this is the RP for this multicast group, and it would do this. It needs to send a packet to this router, and this router, there could be other router in between. There could be other router in between. So how does this router send a packet to that router if they are multi-hops away? If it is multi-hops away, how? You do tunneling, IP tunneling. It means that you put another IP header. So it's the original IP packet has a destination IP address to a class D address, and you put another IP header with a destination IP address to this RP, to this one. So the packet here is IP in IP tunnel to this RP, and then this RP would then decapsulate, and since this router, they know that they also does hashing. They know if this guy send a join message, they know that the RP of this multicast group is this one, so they will send a join message in that direction. They'll also send a join message in that direction, and it will be prompt because this is a duplicate, so it's prompt. Okay, so the RP knows there are members in this direction because some guy just sent me the join message. So I would decapsulate the packet and then send it here. And again, because they keep track of the join message, so they would be forwarded here and here. So then if this is a source, then it would send it to the router, edge router, and the edge router will tunnel the traffic, tunnel the packet to the RP, and RP will encapsulate and then decapsulate and then forward it to the downstream with the join message. With the join state. However, you see immediately, this is not a good path, because these two guys are so just one hop away, but you need to go all the way up and then all the way down to reach this. So there's a short path here. If this guy know, okay, there's a path here, it could be forwarded here without going all the way up. So one improvement is first improvement is that you don't want to tunnel the traffic. You don't want to encapsulate traffic. So you can do this once the RP can send the join message downward, send the group specific join message downward, so that all the router along the path, between them will know this join membership information. So it would send the source specific join message downward. So then again, if you have further packets, then you don't need to do tunnel, because all the router, they know the state, they know the join state, and they will know how to forward the packet. So in the phase 2, you remove the tunnel, no encapsulation, because the router in between, they know the join state. And the phase 3, you want to have a shortcut. You have a shortcut. So this guy could send the source specific prompt and source specific join so that there could be a shortcut in here. So at the end, your message, if this is source, then it will send this way. It will send this way, and here you will split, and then go down here, here, and here. A better path. So it's a. So with this, the advantage of code-based tree is that the path is not as good as source-based tree. The source-based tree has the best path because every source look for the shortest path tree. But in a code-based tree, the path is not as good because you have to share a tree. But there could be some shortcut created so that you would have a little bit better tree. But still, there's basically only one tree maintained.